Hey everyone, and welcome to another deep dive.
Always fun to go beyond the textbook, right?
Absolutely. And today, we're doing just that. We're going to be diving into the world of solid-state chemistry.
Sounds very specific.
It is, but trust me, it's fascinating. We're taking a close look at a lecture from Professor Pedro Camargo at the University of Helsinki, all about defects in solids.
Defects in solids, like cracks and things.
Not quite. These are more like tiny imperfections at the atomic level, and get this, these so-called defects are actually way more important than you might think.
Okay, I'm intrigued. Tell me more.
They're not just unavoidable. They're actually the secret behind some of the most incredible material properties.
Like what?
Think vibrant gemstone colors and the conductivity of semiconductors. We'll be covering all that and more.
Okay, you've got my attention. So why are these defects even there in the first place? I always imagined solids as these perfectly arranged structures, like a flawless diamond or something.
Right, like those satisfying time lapses of Lego builds. But it turns out that's not the whole story. Solids are full of these tiny flaws.
It seems counterintuitive. Why would solids, these models of order, even tolerate imperfections?
Yeah, it's a great question. You'd think they'd always want to be in the lowest energy state, perfectly ordered.
Right. Minimum energy, maximum stability.
But it turns out it's all about balance.
Balance.
Yeah, balance between energy and disorder. You see, systems do tend towards low energy, but there's also this thing called entropy.
Entropy, right. Basically a measure of disorder.
Exactly. And sometimes the increase in entropy from forming a defect actually outweighs the energy cost.
So you're saying these imperfections can actually make the system more stable?
In a way, yes. It's like, think of a line of dancers moving in perfect synchronization. That's low entropy, very predictable. But what if one dancer decides to try a new move, breaking the perfect pattern?
I love that analogy.
Right. So that's our defect. A little bit of chaos that shakes things up, increases the entropy, and even though it might require some energy for that dancer to break the pattern, the increase in disorder can make it worth it.
Okay, I'm starting to get it. So these defects aren't always a bad thing. They can actually add some spice to the mix.
Exactly. Now, the lecture mentions specific types of defects. It starts with these things called point defects. And I have to admit, the names Schottky and Frankel sound a bit intimidating.
They do have a ring to them, don't they?
But they're not that complicated once you break them down.
Okay, good. Let's start with Schottky defects. What are those?
Think of them as vacancies in the crystal lattice.
Vacancies.
Yeah, like missing puzzle pieces.
Okay, so there are just gaps where atoms should be. Doesn't that weaken the material?
Not necessarily. The key with Schottky defects is that these missing pieces occur in a balanced way to maintain charge neutrality.
Charge neutrality.
Yeah, so for example, in a compound made of positive and negative ions, you might have both a positive ion and a negative ion missing.
So it's like a perfectly balanced scale, even with some weights missing.
Precisely. The system is self-correcting, making sure the overall charge stays balanced.
Clever. What about those Frankel defects?
Think of those as an atom or ion playing musical chairs within the lattice.
Musical chairs?
Yeah. It jumps from its regular spot to a different space, called an interstitial site. But the important thing here is that the overall composition remains the same.
So no atoms are actually lost or gained, they're just rearranging themselves.
Exactly. Just a rearrangement, not a change in the number of atoms.
Gotcha. So we've got our missing pieces with Schottky defects and our musical chairs with Frankel defects. Are there other types of point defects out there?
There are a few others, like atom interchange defects, where two atoms simply swap places.
Okay, so basically atoms moving around and sometimes going missing.
Pretty much. But Schottky and Frankel are the most common, and let's face it, the most fun to visualize.
Agreed. Now, the lecture points out something that makes a lot of sense. No solid is perfectly pure. And that's where extrinsic point defects come into play, the world of impurities.
And this is where things get really interesting, because even tiny amounts of impurities can completely change a material's properties.
The lecture gives this captivating example of gemstones. Did you know that the dazzling colors of rubies and sapphires are actually due to impurities?
Wait, are you serious? So those supposedly flawless gemstones are actually flawed?
It's true. Take rubies, for example. They're essentially aluminum oxide, but with a tiny bit of chromium thrown in.
Chromium, like the shiny stuff on cars.
The very same. Those chromium ions sneak into the aluminum oxide crystal and replace some of the aluminum ions. And it's the way those chromium ions interact with light that creates that stunning red color.
Wow, that's incredible. What about sapphires? What gives them that brilliant blue?
Sapphires get their blue hues from trace amounts of iron and titanium, again substituting for aluminum in the crystal structure.
So it's like these tiny imperfections are actually creating beauty.
Mm,
I love that.
me too. It reminds us that sometimes those little flaws can be the most interesting part.
That actually reminds me of something else the lecture mentioned. Doping.
Doping.
Yeah, it's like we're intentionally adding impurities to fine-tune a material's properties, right?
Exactly. Doping is like adding a secret ingredient to a recipe to make it truly shine. We intentionally introduce these impurities, called dopants, into a material, usually a semiconductor, to change its electrical conductivity.
It's a crucial technique in the semiconductor industry.
Absolutely. Controlling those impurities is key to creating the materials that power our electronics.
So these tiny defects we started with have now led us to semiconductors, the foundation of modern technology.
It's all connected.
But before we go full-on electronics, the lecture mentions another category of defects. Dislocations.
Dislocation.
Yeah, imagine a line of dancers where one person is slightly out of step. It disrupts the flow, right?
Right.
And in materials, these linear defects, these dislocations, can affect strength and ductility.
Okay, so even on a bigger scale, these imperfections really matter.
Absolutely. The lecture also touches upon interfacial defects.
Interfacial defects, what are those?
They're basically boundaries between different regions in a solid. Picture those edges of puzzle pieces. They don't always fit perfectly together.
Right, some pieces fit better than others.
Exactly. And these interfacial defects are super important in processes like catalysis.
Catalysis, the speeding up of chemical reactions.
Exactly. For instance, catalytic converters in cars rely on these imperfect boundaries to provide sites where harmful exhaust gases can react and be converted into less harmful substances.
So these imperfect boundaries are actually doing good for the environment.
I love a plot twist. It's another example of how defects can have unexpected and even beneficial consequences.
This is seriously making me rethink everything I thought I knew about chemistry.
I know, right? But hold on, folks, because we're just getting started. We're about to explore the world of non-stoichiometric compounds, where chemical formulas get a little flexible. Get ready for part 2, where we'll discover that sometimes rules are made to be broken, at least in the world of solids.
Welcome back to our deep dive into the hidden world of solids.
It really is hidden, isn't it? I mean,
yeah.
who knew there was so much going on at the atomic level?
Right, and we've been exploring how these tiny imperfections, these defects, actually shape the properties of materials in some pretty fascinating ways.
It's totally changing the way I think about chemistry. Last time we were talking about how impurities are responsible for the vibrant colors of gemstones like rubies and sapphires. It's amazing how something we usually consider a flaw can create something so beautiful.
It is pretty remarkable, and it actually leads us perfectly into the next mind-bending concept from the lecture, non-stoichiometric compounds.
Non-stoichiometric compounds. Okay, that sounds a little intimidating.
It's a mouthful, I know. But the concept itself isn't that complicated. Prepare to have some assumptions challenged. You might think chemical formulas are set in stone.
I mean, that's what we learned in school, right? Like H2O for water, always 2 hydrogens and 1 oxygen.
Right. But it turns out that's not always the case, particularly in the world of solids. Non-stoichiometric compounds can actually have a variable composition while still maintaining the same basic structure.
Wait, hold on. Variable composition. How does that even work? Doesn't a chemical formula tell you exactly what a compound is made of?
You'd think so, right? But imagine a building with a flexible blueprint. You can adjust the proportions of materials a bit while keeping the overall design the same. That's kind of what's happening with non-stoichiometric compounds.
So it's still the same compound, but with a slightly different recipe.
Exactly. The lecture mentions woostite as an example.
Woostite. Okay. And what is that?
It's a type of iron oxide. We usually write its formula as FeO, but the reality is it can have different ratios of iron and oxygen atoms.
So it's still woostite, but with a slightly different flavor, based on the ratio of iron to oxygen.
A good way to put it. And the interesting thing is that those different flavors can actually have different properties. For instance, the electrical conductivity of woostite can change depending on how much iron and oxygen are present.
So this isn't just some chemical curiosity. These non-stoichiometric compounds have real-world implications.
Absolutely. This ability to fine-tune the composition without changing the fundamental structure opens up all sorts of possibilities for designing materials with specific properties. It's a bit like having a slider instead of an on-off switch.
Okay, that's pretty cool. But how is this even possible? Don't chemical formulas dictate the exact ratios of elements in a compound?
You would think, wouldn't you? To answer that, we have to dive into the world of oxidation states, those positive and negative charges atoms can have.
Oh, right, oxidation states. Those were always a bit tricky back in chemistry class.
Well, they're back, and they're key here. In these non-stoichiometric compounds, you can have some atoms of the same element existing in different oxidation states.
So like some iron atoms might have a +2 charge and others a +3 charge?
Exactly. And this allows for those variations in composition without messing up the overall charge balance. It's a delicate dance, really.
So it's like using those different oxidation states to keep everything in check.
Precisely. And it's not just about non-stoichiometry. The lecture also brings up solid solutions, which are sort of like a blend of two or more compounds.
Like mixing paint colors to create a new shade.
Perfect analogy. In these solid solutions, atoms of different elements can occupy specific sites within the crystal lattice, creating a homogeneous mixture.
So it's like a mixed breed dog, a bit of this and a bit of that.
I like that. And the composition can vary within certain limits, leading to a whole range of materials with subtle differences in their properties. We use this concept in countless applications, from alloys to semiconductors.
It sounds like we have a lot more to discuss. We've gone from seemingly simple defects to these complex ideas of non-stoichiometry and solid solutions, but I have a feeling there's still more to uncover.
You're right, there is. And that leads us perfectly into the last part of our deep dive, where we'll be exploring the electronic structure of solids.
Bands and gaps, here we come. And we're back for the final part of our deep dive. It's been quite a journey, hasn't it?
Yeah, we've covered a lot of ground.
From those tiny point defects to those rule-bending, non-stoichiometric compounds,
And now we're going to dive into the world of semiconductors.
which are basically the foundation of modern technology. But before we get into the applications, the lecture takes a step back and explains how electrons actually behave in solids.
Right, it's not as simple as you might think. We have to introduce this concept of bands.
Bands.
Yeah, imagine a crowded stadium where the individual seats merge into continuous rows.
Okay, I can see that.
And those rows are like energy bands in a solid. They're continuous ranges of energy levels that arise from the overlapping of atomic orbitals.
So instead of discrete energy levels, we have these bands.
Exactly. And just like in a stadium, there are different sections, or in this case, energy bands, with different energy levels.
Okay, I'm picturing these bands, but why are they so important?
The key is that these bands are separated by gaps called band gaps.
Like band gaps, okay.
And these gaps are like forbidden energy zones where electrons aren't allowed. Think of it like a no man's land between two countries.
So electrons can be in the bands, but not in the gaps.
Precisely. And here's the kicker. The size of the band gap determines whether a material is a conductor, an insulator, or a semiconductor.
Wait, so the size of the gap dictates how well a material conducts electricity.
Yeah, think of it this way. If the band gap is small, electrons can easily jump from the lower energy valence band to the higher energy conduction band.
And that allows for electrical conductivity.
Exactly. And that's what makes a metal.
Okay, small gap equals conductor. What about insulators? Those don't conduct electricity well at all.
Right. Insulators have large band gaps, like a huge wall separating the valence and conduction bands. Electrons can't easily make that jump, so they stay put, and the material doesn't conduct electricity well. Think of things like rubber or glass.
Okay, so big gap means no flow of electrons, which means insulator.
You got it. So where do semiconductors fit into this picture?
Well, their conductivity is somewhere in between, right?
Exactly. Semiconductors are like the Goldilocks of materials. Their band gaps are not too big, not too small, but just right.
So some electrons can make the jump across the gap, but not as easily as in a metal.
Precisely. At room temperature, a few electrons have enough thermal energy to make the leap to the conduction band, allowing for some conductivity. But here's the really cool part. The conductivity of semiconductors actually increases with temperature.
Really? That's kind of counterintuitive.
Yeah.
I thought things usually get less conductive as they heat up.
It might seem that way, but think of it like this. As the temperature rises, more electrons in the semiconductor gain enough energy to cross that band gap.
Like they're getting a boost from the heat.
Exactly. And that leads to increased conductivity.
Okay, so that makes sense. Now, the lecture talks about different types of semiconductors, starting with intrinsic semiconductors.
Intrinsic semiconductors are the pure, unadulterated versions. They have that temperature-dependent conductivity we just talked about.
And then there are extrinsic semiconductors.
Right. Those are the ones where we intentionally add impurities, those dopants, to fine-tune their conductivity.
Like we were talking about before. So those impurities either add extra electrons to the conduction band, making it an N-type semiconductor, or they create holes in the valence band, which act as positive charge carriers, making it a P-type semiconductor.
Exactly. It's all about controlling those impurities to get the desired conductivity.
And those N-type and P-type semiconductors are the building blocks of modern electronics.
Absolutely. They're the foundation of everything from smartphones to computers to solar panels.
Wow, it's incredible to think that those tiny defects and impurities we've been discussing are responsible for the technology that shapes our lives.
It really highlights the power of understanding and manipulating materials at the atomic level.
Totally. So what are some specific examples of how semiconductors are used?
Well, there are diodes, for example. Those allow current to flow in only one direction, which is essential for controlling the flow of electricity in circuits. Then there are LEDs, or light-emitting diodes. They convert electrical energy directly into light, which has revolutionized lighting technology.
Yeah, LEDs are everywhere these days. What else?
Solar cells use semiconductors to harness sunlight and generate electricity. They're key for renewable energy. And then there's photocatalysis, which uses semiconductors to accelerate chemical reactions. It has applications in environmental remediation and even artificial photosynthesis.
Wow, the impact of semiconductors is truly massive. And it all starts with those tiny defects.
And it doesn't stop there. The lecture ends by taking us to the nanoscale, where we encounter these things called quantum dots.
Quantum dots, okay.
They're tiny semiconductor particles with size-dependent properties. Imagine a painter's palette where the color changes depending on the size of the brushstroke.
That's wild.
That's quantum dots. Their size determines their band gap, and hence the color of light they emit.
So we can literally tune the color of a material by changing the size of the particles.
Exactly. It's nanotechnology at its finest.
This deep dive has been amazing. We've gone from those seemingly insignificant imperfections to groundbreaking technologies.
And it's all thanks to a better understanding of those tiny defects in solids. Who knew flaws could be so fascinating?
It's a great reminder that there's always more to learn, even about the things we think we understand well.
And that the most interesting discoveries often lie hidden beneath the surface, waiting to be uncovered.
I couldn't agree more. A huge thank you to Professor Camargo for this insightful lecture, and to you, dear listeners, for joining us on this adventure into the fascinating world of solid-state chemistry.
It's been a pleasure. Until next time, keep exploring and never underestimate the power of a tiny defect.